Hello, ladies and gentlemen. Welcome to Physics Oscillations question 5. Now, the first question is a simple definition question. State what is meant by simple harmonic motion. Simple harmonic motion is the motion of a particle around an equilibrium position such that the acceleration of the particle is proportional to its displacement from the equilibrium position and is in the opposite direction. You can also say it's directed towards the equilibrium position, always directed towards equilibrium position. The definition of simple harmonic equation can also be expressed as a formula. A equals to minus omega squared x, where A is the acceleration of the body, x is the displacement of the body from the equilibrium position, and omega is the angular frequency. Now we can see that the definition in English and math is the same. Does a ball bouncing on the floor undergo simple harmonic motion? No, it does not, for the two reasons. Now, whenever you discuss whether an object is undergoing simple harmonic motion, you must always talk about, number one, the magnitude of the acceleration. Is it proportional to displacement? So here's a magnitude. And number two, you must also talk about the direction. The direction of the oscillation, the acceleration. Since the magnitude is not proportional to the displacement from equilibrium position, and furthermore the direction of the oscillation is not directed to the equilibrium point, so it's not a simple harmonic motion. Okay, so you see how everything ties into the definition. Alright, for question 5D, this is the object undergoing simple harmonic motion. Let's determine the period. Now when they give you three waves, you should use the period for the entire graph. So the period will be 0.12 divided by 3, which will give you 0.040 second to 2 SF. Okay, so this is part 1. Part 2, frequency is 1 over period, 25 Hertz. Now, over here, you can see the acceleration is 50 meters per second, and that's the maximum. So A maximum is equals to the magnitude of omega squared x maximum. Now, in order to find the amplitude, x naught will be equals to A0 divided by omega squared. Okay, and you can easily calculate that out. 50 divided by 157 squared is 2 times 10 to the power of minus 3 meters. So the object oscillates by 2 mm. Now, so sketch and label the acceleration displacement and velocity displacement graph. The acceleration displacement graph is given by the following. Now the maximum acceleration is over here. Something is not right. Okay, the amplitude is 2 meters, 2 millimeters. So this is 0.002, 0.002, and 50. Okay, so this will be the acceleration with displacement graph. The velocity of displacement graph will be as follows. Now, how do we find out the maximum velocity? The maximum velocity will be equals to the omega x naught. Okay, where do we get this from? Well, remember, x is equals to x naught sine omega t. How do we obtain velocity? By differentiating the displacement with respect to time. So that velocity will be x naught omega cosine omega t. And the coefficient will be the maximum velocity. Alright, this is V naught. Okay, so now we can just multiply those two terms together to get these 4 points. Whenever you plot down the graph, you must fill in all the details that I've put into the boxes over here. Firstly, you must have the axes labels. Alright, number 2, you must have the intercept labels. Okay, for each of the intercept. So these are what you need to draw in order to get the points for the graph. Now let's take a look at question 6. Question 6 is about a metal plate with an object oscillating on top. Now you can take a look at this A and Y curve. What does this curve tell you? This curve is this line is A is equals to minus omega squared x. So over here you got to read. This one will be x naught is equals to 8 times 10 to the minus 3 meters. Then what about A maximum? Let's take a look at A maximum very carefully. it looks like A maximum is over here, right? A max is over here, which we draw a straight line. Ta-da! Okay, it's about 4.5 meters per second. This means that A maximum is equals to 4.5 meters per second squared. Now, what this also tells us is that we can obtain omega almost instantly. The maximum value of A will be omega squared x naught. So that means that omega squared is equals to, okay, rather we just do a shortcut. Omega is equals to A naught over x naught square root. And that gives us 23.7 radians per second. Alright, so in every simple harmonic question, let me guarantee for you that you will need to find omega. Alright, confirm plus guarantee that this is the way to do the question. Yeah, I haven't even read the question yet, and already I've got so much information from the graph. Now, sand is sprinkled on the plate. Okay, use figure 6.2 to show how it can be deduced that the sand is undergoing simple harmonic motion. Now, for this one, you need to actually write 4 different points. Okay, let's write the point 1A. The point 1A, you must show that the graph is a straight line through the origin. Now, what does this show? Now, this shows that, okay, so 1B shows that the acceleration is proportional to the displacement from the equilibrium position. And then you must write again 2A. This is the second thing that you must write. The graph has a negative gradient. And what does this show? This shows that the acceleration and displacement are in opposite directions. Once again, this is the definition of SHM. The definition of SHM is that the acceleration is proportional displacement for equilibrium position, but they are in opposite directions. Okay, so this must be how you do it. Okay, so all these 4 points go to 2 marks. Now calculate the frequency of the sand. The frequency of the sand is easily done because we have omega is equals to 27.1 radians per second as above. Okay, as above. Right, so then we can find omega. The frequency is easily found over here. F is equals to 3.8 hertz. Okay, now let's take a look at B part 1. The amplitude of oscillation is increased beyond 8 mm. At 1 amplitude, the sand is going to lose contact with the plate. Where is the plate and what is the amplitude when the sand loses contact? I'm so sorry, I just realized that I made a boo-boo over here, a mistake. The omega is not 27.1, it's 23.7 over here. Right, so this is 23.7 radians per second, and the frequency is 3.8. Okay, let's go back to part B. Now, I want you to take a look, all right, at this object that I have in my hand. Now, this is just a power brick that I have in my hand, all right. It's loosely on my palm, so it's free to move. Now, when I move my palm up and down, all right, it still stays on my hand, but as I move it up and down with greater amplitude, there is a point at which it leaves my hand. So when does the block leave my hand? Well, the block leaves my hand when my hand is at the top of the motion. Okay, leaves my hand when the block is at the top of the motion. But why does it leave my hand in the first place? Now, if I hold my hand still and then move it down very quickly, do you see that my hand actually moves first and moves faster than the block? My hand moves first and moves faster than the block. Okay, well, of course, when I move my hand up, there's no such problem. But when I move my hand down quickly, the block separates. Now, okay, let's see what's happening here. Now, because the block is not held by anything, the maximum acceleration of the block will be 9.81 meters per second squared downwards. So this is my hand. Okay, this is my hand over here. This is my hand. But what if my hand's acceleration is more than 9.81 meters per second squared downwards. What if my hand's acceleration is 10 meters per second squared downwards? Now, if my hand's acceleration is 10 meters per second squared downwards, then my hand will move faster than the block. So the block is trying to accelerate, but it can't accelerate as fast as my hand. Then the block will separate from my hand. So once again, in order to get the block to separate from my hand, all I have to do is my hand must move at an acceleration greater than 9.81 meters per second squared. So let's take a look at the answer for this one. When does the sand first lose contact with the plate? The plate must be at the highest position of the plate, and the plate is moving downwards. Okay, so the plate must be at the highest position of the plate, and the plate must be moving downwards. That is when the sand loses contact with the plate, because the sand is not able to accelerate faster than 9.81. Okay, let's calculate the amplitude of oscillation. We'll take a look at part 2. Okay, so when the sand loses contact with the plate, when the magnitude of the acceleration is 9.81 meters per second squared downwards. Okay, so we'll just put in the value A is equals to or greater than omega squared y naught. Alright, so then we'll put 9.81 is greater or equals to 2 pi times 3.8 frequency squared, or you can use the other value like 157 multiplied by y naught. So y naught must be equals to or greater than 17 mm. Okay, so when you oscillate more than 17 mm, then the sand will not be able to catch up with the plate when it's going down. Of course, when it's going up, there's no problem. Okay, so if you don't understand this, ask me again in class. Okay, let's move on to question 7. Now, in question 7, this cylindrical tube floats upright in a container, in a liquid, and is going up and down. Derive an expression in terms of the upthrust and weight for the resultant force acting on the tube when the displacement of the tube is x. Explain your working. Now, first of all, let's consider that there are two forces acting on the on the container. All right, when the container is inside the water. Now, this is the water level. Okay, that's the container. Now, first of all, there is the weight of the container is acting downwards, mg. Then after that, there is an upthrust acting upwards, mg, u. Now, we know that the upthrust is equals to the volume of water displaced multiplied by the density of the water multiplied by 9.81. Now, what is the volume of water that is displaced? Volume, V. Now, the volume V will be equals to the cross-section area A, okay, multiplied by the length of the tube multiplied by any additional length of the tube, okay, L plus X. Okay, this will be the volume. So once again, this will be the area, the cross-section area of the base. This is the area A. Okay, this is the length of the tube that is inside the water. And then when you pull it down a bit more, this is any additional length that is inside the tube, inside the water. So the upthrust at a displacement x will be equals to A multiplied by L plus X rho G. Okay, that's fine. That's fine, huh? Okay, what happens when x is equals to 0? When x equals to 0, the object is in equilibrium. So this is the equilibrium position. Okay, so that means that the upthrust when x equals to 0 will be AL rho G, and the upthrust will be equals to the weight, mg. That's great. Okay, now, so what happens when the upthrust is more? Okay, so let's say we pull it all the way down. We pull this object all the way down so that this is the original length L plus X. Okay, now what happens is that the weight still remains the same, but the upthrust will be much higher. Okay, so this is upthrust at x. So what we can write is this. When the object is displaced down by x, then the upthrust will be equals to AL plus x rho g, and the upthrust exceeds the weight, so the net force will be equals to upthrust minus mg upwards. Okay, and this can be simplified but expanded as the following. Substitute that in: AL plus x rho g minus mg. So we expand it again: AL rho g minus mg plus AL AX rho g. Okay, so let's take a look. Remember that when x is equals to 0, the object is in equilibrium. Okay, when x is equals to 0, right, then the object is in equilibrium. AL rho g is equals to mg. Right, so look at this. AL rho g minus mg, cancel these two. These two will be equals to 0. So the magnitude of the net force when it is displaced by a small distance x will be A rho gx. Okay, but that's not all. Okay, that's not all. So what happens is that when x is downwards, F net is upwards. So that means that the net force on the body will be in the opposite direction to x. Okay, so the net force on the body will be minus A rho gx. Okay, so show that the acceleration of the displacement, so this is part 1, okay, this is part 1. And then using the expression, show that the acceleration will be given by rho ag over mx. Now, for part 2, we can show that F net is equals to ma, right? So A is equals to F net divided by m, which is A is equals to minus A rho g divided by m multiplied by x. Okay, so this is shown. Now, next, did you know that this equation is simple harmonic? This is SHM. How come? It's SHM because this is a constant. Now, if this is a constant, it shows that A is proportional to x, but in the opposite direction. So what do we need to do now? Now, let's take a look. So this means that, therefore, if you compare the two SHM equations, A is minus A rho g over mx, and A is equals to minus omega squared x. It shows you that omega squared is equals to A rho g over m. Okay, or, okay, we can get the frequency, we'll do some math here, is 1 over 2 pi square root A rho g over m. Okay, so let's fill in all the values. You should get frequency is 1.1 Hertz. Okay, so this is the complete solution for the question. Now let's go through the solution again. For an object floating in the water, there are two forces acting on it, the upthrust and the weight. The upthrust is given by volume of the displaced water multiplied by the density of the water multiplied by 9.81. Now, the upthrust when you pull the object down by a small distance x will be AL plus x rho g. But when the object is in equilibrium position, then x is 0, the upthrust will be AL rho g. And since it's in equilibrium, this upthrust equals to the weight, so the object is not going to accelerate. So let's now compare. When the object is displaced down by x, the upthrust increases to a L plus x rho g. Okay, the net force will be upwards because when you pull the object down and you let go, it's going to shoot up. So the net force is upwards. A L plus x rho g minus mg. But wait, A L rho g is equal to mg. So the net force will be A rho gx. That's the magnitude only, okay? We know that when you pull the object down and let go, the object will shoot up. So when the displacement is downwards, the net force is upwards. So we put in the negative sign, that the net force and displacement are opposite directions. Next, we know that the net force is ma, so we can get the acceleration by dividing by m. And we know that this is an SHM because A rho g over m is constant. So it looks just like the SHM equation. And then from here, we can find omega. Didn't I tell you that for all simple harmonic motion questions, the key is to find omega? Okay, and that's question 7. Now let's go on to question 8. Before we begin question 8, we need to first draw the position of the pendulum at time t equals to 0. Now this is the pendulum, okay? It's given a small displacement. It's given a small displacement and then it's released at time t equals to 0. So that means at time t equals to 0, it's over here. Then it goes over here and then it comes back. That is time t equals to the period. Okay, so the period is 2 seconds. So this is 2 seconds. So over here, t is 1 second. So far, so good. That means over here, t is 0.5 and t equals to 1.5. So let me take you through how the pendulum oscillates. Okay, it's given a small displacement, and then over here at t equals to 0 is let go. So it goes to the middle, half a second, 1 second, 1.5 seconds, 2 seconds. Okay, the amplitude of oscillation is 0.3 meters. So this is x naught is 0.3 meters. Now, let's draw the variation of the kinetic energy EK with time. Now, we know that for the kinetic energy, it must be a double hump graph. That means to say that it's 2 humps for every period. Why is that the case? Now, let's draw the kinetic energy with time. Let's do it at the start. At the start, on the left, when you let go, the KE starts from 0. This is the KE. Now, this is 1 second, 2 seconds. At half a second, the object is moving very fast. So the KE will be up here. At 1 second, the object is moving stop. Then at 1.5 seconds, this is the KE. And then this is at 2 seconds. So this is what the KE looks like. Okay? This is the KE graph. Now, usually we will need to write to do the KE a couple of times, but never mind. Okay, we'll just do it over here. Now, what about the total energy? The total energy will be a straight line over here. Total energy. Then the potential energy graph will be the KE graph reversed. So I like to first mark out where all the points are so that I will draw a nice graph that goes through halfway. Okay, so you must try to draw a regular shape graph. This is a PE graph. Ta-da! Now we need to find the maximum value of the total energy. For those of you who have been following my lessons, the total energy will be given by half m omega squared x naught squared, and we fill in the value that is 0.22 joules. Okay, so that will be 0.22 joules over here in joules, and then time is in seconds. So this will be 0. Okay, so that's it. I don't think there's any more work to be done for question 8. So let's move on to question 9. A particle of a mass 90 grams undergoes simple harmonic motion. The graph shows the variation of time with KEEK. Determine the maximum acceleration of the particle. Now this is a rather interesting question. Okay, so we know that this graph here, half m omega squared x naught squared is equals to 0.30 joules. Okay, so what can we tell from this? Okay, now we also can look at the graph over here. 2 complete humps is 1 period. So t is equals to 200 times 10 to the power minus 3, or rather t is equals to 0.2 seconds. Okay, so from these two, we can obtain this information. We can find omega. Omega will be equals to 2 pi divided by t. This will be 31.4 radians per second. So over here, half of the mass, 0.90, 90 grams, and then it's 31.4 squared. X naught squared is equals to 0.30. This means that X naught is equals to 0.0822 meters. So now we have omega and we have X naught. What about the maximum acceleration? A naught will be equals to omega squared X naught, magnitudes. Okay, the maximum acceleration will therefore be 31.4 squared multiplied by the the amplitude. That will be 81 meters per second squared. Done. Okay, so that's questions 5 through 9. I hope you enjoy your holiday. See you, bye-bye.